Welcome back, everybody. Hope everybody's having a good day at home. If you're at home, shout out Jennings. Jennings, hope you're watching. Jennings, the code word is. What should the code word be? The code word is monkey. The code word is monkey. No, monkey. Monkey.
I like baloney.
All right. Here we go. So again, just like I said, we're going to jump into section 7.5. How did we feel about the quiz yesterday? Was it on the easier side?
Yeah.
I hope it was. Then you never know. So hopefully that was all right. I will say, in my opinion, the second half of chapter 7 is a little bit more difficult than the first half of chapter 7. But however, I still think chapter 7 in total is on the easier side of the rest of the stuff that we're going to do this year. Okay. We're still on that like plateau, and I made that diagram of how difficult the class is going to be the rest of the year. We're like still on a little bit of a plateau.
Can you redraw the diagram?
What's that?
Can you redraw the diagram?
Can I redraw the diagram? I would say it's like, okay, so if this is time, this is the second semester, and this is difficulty.
Yay.
Always label your X's. Always label your
thank
X's.
you.
This is the total second semester. You know, like, this was,
Oh, you didn't put the title of the graph?
Oh, slacking.
the title of the graph is Student English.
There we go. Well, that
Okay,
was
I would say, chapter 6, in my opinion, was a little bit difficult, so the difficulty went up a little bit. This is chapter 7. Right, that was chapter 6. This is second semester. Look at the timeline, Joy. Look at the timeline. This is chapter 7. Yeah, we're kind of in this plateau. Here's chapter 8.
Oh, no.
Yeah. Here's chapter 9. And then we jump into chapter 13. No, I'm just kidding.
13.
Yeah, I know. We don't do chapter 10 or 11 or 12. We got to get to trigonometry before pre-calc. So, but chapter 13's, I wouldn't say it's that difficult. I would say it's more like,
Just has a straight line up.
moderately difficult.
So,
And then there's a little bit of hard part at the end. Yeah, I know, but I'm just telling you, like we are, like,
None of went down.
you are here.
None
Yeah?
of them like went down.
No, that's true. They're not going down. Okay, so we're kind of in this like little plateau, a little bit of, it's not necessarily getting more difficult. It's just learning new things. Logarithms is just learning all the rules for logarithms, right? So in section 7.5, the total of section 7.5, we're going to spend it in 2 days, is exponential logarithmic equations and inequalities. We're going to spend a day talking about equations, and then on Monday we're going to talk about inequalities. We'll do 2 days on section 7.6 where we get to learn about a natural log, which is really fun. And then we do section 7.7 and 7.8, which are the sections where we transform and then do regression. Just like we've been doing all year with all of our new functions, we're going to transform them, we're going to do regressions on them. The nice thing, you guys are going to like transformations with these things because there's not much to, simplify with them. Think back to the polynomial chapter where you had to like multiply everything out and it got a little bit kind of difficult there. Yeah, there's nothing to do with that. It's really just kind of like putting the operations in and just letting it be. So it's not too bad. But let's talk about exponential and logarithmic equations and inequalities. Now, an exponential equation, this is a very stupid definition. An exponential equation is an equation that contains an exponent. Seriously, come on, your English teachers would hate that. Is an equation containing one or more expressions that have a variable as an exponent. Now, I'm going to give you a variety of methods to solve exponential equations. The thing that you guys will not like about this, and contrary to popular belief, you guys like to be told what to do and how to do it. There's like a variety of different ways to solve these problems. Yeah, and that's what's going to make you guys struggle a little bit. There's no one way to do these problems. I kind of liken this to, you know how sometimes in proofs it was difficult because there was no one route to take. You could take your own route to the final answer, right? That's kind of like the same thing here. There's no one route to take for exponential equations. So I'm going to give you, things to put into your mathematical tool belt, and then you can just use them as necessary. So first way of solving exponential equations. Try writing them so that the bases are all the same. Okay? If we've got sides of the equation that have bases, try writing them so that the bases are the same. Because if you can make the bases the same, you can set the exponents equal to one another. Let me repeat that. If you can make the bases the same, you can set the things in the exponents equal to one another. The second route to take would be to try to take the logarithm of both sides. Try to take the logarithm of both sides. You can take, since the logarithm is an operation, just like you can multiply something to both sides of the equation, just like you can subtract something to both sides of the equation, you can take the logarithm of both sides of the equation. You just have to take the logarithm with the same base. Like you can take log base 10 of both sides. You can take log base 3 of both sides. Because again, it is an operation, so you can do that, and it's not going to change the outcome. It's still equivalent. Last thing here is to rewrite the in either logarithmic form or exponential form. Yeah, change the form, and it might let you solve the equation in a different way. Okay. And then we have our formal definition of a logarithmic equation as well. Again, stupid definition here. A logarithmic equation is an equation that contains a logarithmic expression. Basically, we can solve logarithmic equations by using the properties of logarithms. That's the only thing that we're going to add in there. Being able to use the properties of logarithms will kind of push us on our way toward our final answer. What are the properties of logarithms? Well, when we add, we multiply within the logs. When we subtract the logs, we divide within the logs. When I take a power outside of a log, or of that of number, we can bring it out front and multiply toward that log. So then we, can use those to try to reduce it down a little bit. One thing just to make note, I know some of you guys like to plug your answers back in just to make sure that you got the answer right. Just remember, we're going to be rounding a lot because we're going to be working with logarithms. When you use a rounded answer and put it back into your equation, if you've rounded your answer, obviously it's not going to come out exactly left side to right side. Just to make sure it's reasonable. Like if you get 3.999 and 4.1 on the other side, yeah, that's probably the right answer. Yeah. Okay, so solve and check our answer. Now there's a variety of ways that we can do this, right? I've got 3 to the 2x is equal to 27. Let's go with the first route. Make the bases the same. This is making the bases the same, something that only works certain times. Like for example here, can I take 27 and make that as a base of 3? 3 to the what power is 27? 3 to the third power is 27, right? So 3 to the 2x is really equivalent to 3 to the third. And when I make the bases the same, I can set the exponents equal to one another. So this quite simply becomes 2x is equal to 3, so x is equal to 1.5, or 3 halves. Pretty simple, right? I gave you a simple one because I want to show you a different method as well. What I can do here, I can take the log base 3 of both sides. Right? That's the next one, right? Yeah, take the logarithm of both sides. That's the next route to take. Why did I strategically pick log base 3? Well, because these both can be made out of a base of 3. Log base 3 of 3 to the 2x is equivalent to log base 3 of 27. All right, what happens here? Log base 3 of 3. What happens? That cancels, right? That's that special unique rule where it cancels just to become 2x. And then we can evaluate log base 3 of 27, which is 3. 3 to the third power would be 27. So we get 2x equals 3, x equals 1.5 again. We could have also taken the log base 10 of both sides if we really wanted to, because our calculators work in log base 10. Now, what's the third route? The third route to take is rewrite from exponential to logarithmic form. Notice that this is an exponential expression as it sits right there, right? So let's take that exponential expression and turn it into a logarithmic expression. So, do our spiral, log base 3 of 27 is 2x. Log base 3 of 27 is 2x. And now we can evaluate log base 3 of 27. Log base 3 of 27 is 3. So we get this whole 3 is equal to 2x again. So 1.5 is equal to x. You see how all of these routes get us to the same location? That's going to be true for a lot of these. Now, sometimes you're not going to be able to make the basis the same. Sometimes you're not going to be able to transform it in from log to exponential. So you just got to go with whatever sticks, whatever works. Okay? Let's try to take a look at the next one. See here, can I possibly make the basis the same? Can I take 5 and make it out of a base of 4? No, I can't take 5 and make it base 4. So I've got to do something else. Well, I see an exponential equation, so maybe I'll just turn it into logarithmic. Let's see if that works. Log base 4 of 5 is equal to x minus 1. Log base 4 of 5 is equal to x minus 1. Now, you guys have your calculators. Can you evaluate log base 4 of 5? Yeah, you can. Go ahead and do it. It's going to be decimal. That's okay. See, me and my calculator, me and Joy at least, have to do the change of base formula. That's okay, though. We can do that. It's no big deal. You know why I couldn't give you, you know why it had to be mental math last quiz? Because these calculators do logarithms. There is a log button on there. It's within, there it is, log, right
I know
underneath
we're
second.
smart, but we would not do that.
And I just wanted to give you mental.
We're just kind of dumb in that way.
Do it so that you have enough. We do it for you to put it on.
I hit math. And then scroll down, do you have a log base function?
Plastic shell.
See, for me, I've got to go in and say, I can evaluate log base 4 of 5. I can turn that into a decimal. I'll have to do log of 5 divided by log of 4. You can actually go in and change the base. So 1.16 is equal to x minus 1. Now, did I round that answer? Yeah. So when I go back in and I check if I'd like to do so, I'll just have to know that it's not, maybe not going to equal 5 right on the dot. Add the 1 over to the other side, 2.16 is equal to x. See, if I go back in and I evaluate 4 to the 2.16 minus 1, that's not going to actually equal 5. It's going to get close to 5, but it's not actually going to be 5. That's okay. Because I rounded my answer. Okay, questions about that? All right. Take a look at this one. There's 2 routes to take here, but I'm going to do the one where I have to make the bases the same. Can I make 8 out of a base of 4? 4 to the what power is 8? No, I cannot make 8 out of a base of 4. People always try to make 8 out of a base of 4. Can't do that. But can I make 8 out of a base of 2? Yeah. Can I make 4 out of a base of 2? Yeah, so let's do that. I know that 4 is really 2 squared, and I know that 8 is really 2 to the third. Now, the thing is this is 2 to the second to the 3x minus 1. This is 2 to the third to the x plus 1. What do I have to do with those exponents? What do I have to do? I have to multiply them. Right, exactly. All right, so I multiply in, I distribute to this, and I get 6x minus 2. This is 2 to the 6x minus 2. And this is 2 to the 3x plus 3. Now, again, once you make the bases the same, you can set the exponents equal to one another. So I've got 6x minus 2 is equal to 3x plus 3. Everybody follow me there? And now I've got a pretty easy equation that I could solve for x. Subtract the 3x, add the 2, so x is equal to 5/3 or 1.6 repeating. Okay. I could have also taken the log of both sides. I could have done that. I could have taken log base 2 of both sides if I really wanted to. I wonder if this will work. I'm just kind of throwing something at the wall here. Let's see if this is actually going to do something. Because I see something that, is in exponential form. This is 8 to the x plus 1. I didn't try this ahead of time, but what if I tried to turn this from exponential into logarithmic? Because the other side is really just 8 to the x plus 1. So let me see if this works. I don't even know if this will work. I would say log base 4 of 8 to the x plus 1 is 3x minus 1. Yeah, this is going to work. Why? Well, what can I do with the x plus 1? If it's in an exponent, what can I do? Bring it out front and multiply. So this is really x plus 1 times log base 4 of 8 is equivalent to 3x minus 1. Can I evaluate log base 4 of 8? Sure, I've got my calculator. I've got to do change of base, so I'm just going to do log of 8 divided by log of 4. And I'm going to get 1.5. X plus 1 times 1.5 is equal to 3x minus 1. And now I've got a simple linear equation to solve. I distribute into 1.5. 1.5x plus 1.5 is equal to 3x minus 1. Subtract over, add over. 2.5 is equal to 1.5x. 2.5 divided by 1.5 is 1.6 repeating. Yeah. So that was 1.6 repeating. That was kind of a weird way to go, right? Changing something from exponential into logarithmic form that didn't necessarily look like it was exponential. Okay? As long as you have one of the sides of the equation that has an exponent and the variable's up in the exponent, you should be able to change the form and see if something works out in the end. Okay? Let's keep it going. Oh, sorry, did you need that? There you go. Okay, looks like I've got log base 6 of 2x minus 1 is equal to negative 1. So now I'm starting with logarithms. I'm starting with logs, and I'm working to find the number. You good? Okay. Now, obviously, taking the log of both sides is not really going to do anything here. Trying to make the bases the same, well, they're not exponential, so that doesn't really work either. So maybe I want to change it into exponential. Let's see if that works. Okay, log base 6 of 2x minus 1 is equal to negative 1. That means that I can take this 6 as my base, negative 1 is the exponent, and it's equal to 2x minus 1. All right, so 6 to the negative 1 is equal to 2x minus 1. And now I can solve that. 6 to the negative 1 is 1/6 is equal to 2x minus 1. So I add 1. What's 1/6? 0.16 repeating. So I add 1.16 repeating. I divide by 2. Let's see what that is divided by 2. Add 1, divided by 2. 0.58. Okay. That was a pretty simple, just change the form. When you're given a logarithm, Try to change the formula to an exponential, see what happens. It might be solvable pretty easily. 0.58, yeah. You know what else I could have done? You know how I can take the logarithm of both sides? You can actually take both sides as a base of the same number. Okay? Watch this, everybody. Watch this. I could have also done this. Taken both sides as a base of 6. Why am I doing that? Because look what's going to happen on my left side. I took everything up here. That was my original equation. I put everything up in an exponent as a base of 6. Because what's going to happen over here? 6 to the log base 6. That's going to cancel. So that's going to be 2x minus 1 is equal to 6 to the negative 1, which is the exact same thing that we ended up with here. And then the work is the same for that. Let's take a look at another one. What you guys have, right? Log of 3x plus 1 minus log of 4 is 2. All right. What is subtraction of logs? Division within the log. Okay, what does that mean? That means I've got log of 3x plus 1 over 4 is 2. And now I've reduced it down to 1 log. I can turn it from logarithmic form into exponential form. What's the base of this log? 10. So that means I've got 10 squared is equal to 3x plus 1 over 4. Oh, that's not bad at all. 10 squared is just 100. So 400 is equal to 3x plus 1. Subtract the 1. Divide by 3. So you try to reduce it down into something that's linear, something that's solvable, something that's a little bit easier to solve by doing one of the methods. Okay. We had to reduce it down to a single logarithm to try to work with it, to try to put it into exponential. Okay. I'm trying to see if I could have done something else too. No, I won't even go that route. Here's an issue though. Watch out for calculated solutions that are not solutions of the original equation. You know how I've been telling you to check your answer every time? That's because sometimes when doing the operations with logarithms, what are called extraneous solutions might come up. Ones that look like solutions when I solve it using our algebraic methods that are not actually solutions of the equation. Let me show you what I mean here. What does addition of the logs mean? Multiplication, right? So this is really log base 12 of x squared plus x. All I did was just distribute, right? I would take x times x plus 1, which is just really x squared plus x. All right, and now I change it from logarithmic into exponential. 12 to the first is equal to x squared plus x. And now this is quadratic. So I've got my 3 options. I've got quadratic formula, completing the square, or just plain old factoring. 0 is equal to x squared plus x minus 12. And does that factor? Yeah. Positive 4, negative 3. Or no. Yeah, I was right. Positive 4, negative 3. 0 is equal to x plus 4, x minus 3. Factors that multiply to get the negative 12, but add to positive 1. So my solutions of this equation are x equals negative 4 or x equals 3. Now, let me ask you something. What is the domain of a logarithm? What is the domain of a logarithm? Think about the x values. can never be negative. The x values can never be negative. Remember our graph of a logarithm? Just a plain parent function looked like this, right? Doesn't curve back around, go straight down. But does it ever go into the negatives for my x value? No, negatives don't compute. Right? Negatives do not exist. Okay, which answer gets thrown out? -4. -4 gets thrown out. My only answer, therefore, is x equals 3. Okay. How else could you have seen that if you didn't remember the thing about the domain of a logarithm? Well, if you would have tried to go back and plug it in, you would say, okay, log base 12 of -4. And if you guys try to type in log base 12 of -4, it says error. It says domain error, because it's not within that domain. When you try to evaluate the log of a negative number, it will give you an error. It will give you an error. The reason being it's not within its domain. 3 is fine. Okay? I can evaluate 3, because this is going to be log base 12 of 3 and log base 12 of 4. Okay? And then that would add together to get 1. But I cannot evaluate log base 12 of -4. I wouldn't have been able to evaluate it here as well, because even though I added to it, it's still going to be negative when I go to take the log. So that's the extraneous solution there. Let's do another one like that. Log base 4 of x minus 1 plus log base 4 of 3x minus 1 is equal to 2. All right. So I see the same log base, so I can multiply these things together, right? I can take log base 4 of, and I'll write it out here, x minus 1, big parentheses, x minus 1, 3x minus 1 is equal to 2. Just showing the word. I got to FOIL this. I know that. So log base 4 of, okay, first, 3x squared outer minus x inner minus 3x plus 1. So log base 4 of 3x squared minus 4x plus 1. Because addition meant to multiply. All right, so now I change it from logarithmic form into exponential form. I take this logarithm base 4, so it's 4 to the second power, is equal to this thing inside the parentheses, this 3x squared minus 4x plus 1. Log, or 4 squared is 16, right? Let's rewrite that, 16. Subtract over the 16, make it equal to 0. Always got to set it equal to 0 to be able to do the zero product property. 1 minus 16 is -15. And now, does that factor? Some of you guys might not even want to try to factor it. Some of you guys are so good at the quadratic formula now that you're like, I'm not going to do the quadratic formula. But for old time's sake, let's factor this. 3 times -15 is -45. Are there factors in -45 that add to get to -4? Yeah, -4, -9 and 5. Yeah. You know, it's really because look at what I'm doing in Algebra 1. I'm like teaching this exact thing in Algebra 1. So. Oh, factor. So I rewrite. Factor by grouping. Pull out a 3x. Oh, wait. X minus 3. Jeez, what the heck am I doing? I combined those two things. Just x minus 3. Get ahead. All right, so we've got an x minus 3 and a 3x plus 5. So that means we've got an x equals positive 3 and an x equals, subtract the 5, divide by 3, -5/3. Now, be careful if you just go ahead and throw out the negative. I got to be honest, a lot of the times you just throw out the negative. However, go back in and see if you plug it in, will it be negative? Like if I look at 3, positive 3, does that ever turn out to be negative when I go to evaluate the log? No, 3 minus 1 is 2, So I'm good there. I can evaluate log base 4 of 2. 3x minus 1. So 3 times 2 is 6. 3 times 3. 3 times 3 is 9. Minus 1 is 8. I can evaluate log base 4 of 8. But can I evaluate this negative 5/3? No, because negative 5/3 minus 1 only gets me more negative, and that right there is not a solution. I don't even need to check the other piece of this. I know that I'm going to try to, when I plug in negative 5/3, it would make me evaluate a negative number, and I can't do that. So therefore, I do throw out the negative 5/3. My only solution here is an x equals 3. Okay. So when do you need to check for extraneous solutions? Well, when the initial problem has a logarithm in it. That's when. Because the domain of the logarithm is restricted to only being positive, any negative solution that you would get, you have to check. Because if you go back in and you would go to evaluate a negative in the logarithm, got to throw that answer out. Now be careful there. You know, if I had gotten like a -1 as my answer, but then I would go back in and maybe inside the logarithm it would turn it back positive all the time, well the -1 would still be a solution. Because when I would go to evaluate the logarithm, it would be a positive number in the end. So you just have to check based on the context of the original problem. Would I actually have to evaluate the logarithm of a negative number? And if I do, I throw that answer out. If not, then I'm good with my answer. So tomorrow we will look at solving exponential logarithmic inequalities when you see whether it's greater than or less than rather than just equal to. All right. So long, everybody at home.